Knowledge engineering is a broad term for the codification of expert knowledge into interactive databases that present that knowledge in a consistent and canonical manner to users. For example, an expert in horticulture might use knowledge engineering to encode the rules and heuristics with which they would be able to identify a particular plant species from a fragment of plant material. Typically, a subject matter expert would employ a general programming language such as Prolog, or a domain-specific language such as Clips, in order to define and execute the deductive rules necessary for inference. The resulting system would allow users to answer guided sequences of questions with the ultimate goal of correctly reproducing the expert's answer to a complex query, such as medical diagnosis. IfWizard's invention is designed to make it much easier for subject matter experts to turn their human knowledge into computerized functional information. In particular, the invention is designed to allow the development of knowledge-based systems without prior computer programming or computer-aided software engineering experience. Instead of centrally placing the mathematical rules of deduction used by conventional inference engines, the IfWizard system refocuses knowledge engineering on the readily understandable activity of answering sequences of user-facing questions. In the IfWizard system, the knowledge is stored as a set of pages, of which a single page is shown to a user at a time, and between which navigation is typically responsive to a user's answers. For example, answering yes on one page may lead the user to a particular destination page, while answering no may lead them to a different destination page. Each page is designed in such a way as to guide the user in answering a stage of questioning. Pages have content section or sections which are intended to provide a complete and user-friendly explanation of and instructions for answering the questions which follow in the interface section or sections. The interface's individual questions are presented to the user through widgets, which largely match a specific type of question such as true or false or text input. Once the user has entered their answers into the widgets, the page's results execute one or more specific actions such as setting a variable which will be available to other pages, or navigating to another page. With each page, the contents, interfaces, widgets, and results may be conditionally present based on testing against variables, allowing, for example, a single page to display variations depending on the user's prior answers. Once the expert has completed entering in their knowledge, the expert may easily produce a working knowledge base for users that may be readily distributed and shared. This working knowledge base contains a player that performs all of the necessary procedures for the pages, contents, and so on to be appropriately presented to and analyzed for the user. By reconsidering knowledge engineering through this highly user-centric creative process rather than the traditional deductive logic method that evolved from declarative programming, it is hoped that a larger and more diverse population of subject matter experts will be able to share and utilize their specialized knowledge.
In this demonstration, we'll use IfWizard's knowledge engineering invention to create an automated underwriting system. To begin, we'll create a variable to track the borrower's candidacy through points. Now let's create a few pages to gather information from the borrower about their application, storing their answers in variables that may be evaluated or saved later on. Some information gathering pages are only shown if the borrower selects certain answers. For example, if the borrower chooses Other as the type of mortgage, they must elaborate on an additional page. We'll test our system at this point to confirm this. Now we'll create a similar page for the terms of the requested loan. Again, depending on the amortization type, additional information may be requested of the borrower. We use conditions that test for the interface amortization widget's result to route the correct destination page. Once we have added sufficient information gathering pages, we are ready to evaluate the loan application. Once the borrower formally signs and submits their application, we test it against any rejection flags that have accumulated through the process. We can also use externally provided functions for complex or proprietary algorithms to determine eligibility, as here, where the application is further tested by evaluating PITI to income and debt to income ratios. If no outright rejection occurs, the application may have been flagged for manual review by an underwriter. If no rejection or manual review occurs, all conditions have been satisfied, and the final matching result is loan approval. Details about the loan and other information may be processed along the way mathematically and in other ways as part of the evaluation. Additionally, our system asks the user for declarations that can flag the loan either for rejection or manual review. In this case, note that some of the declarations increment the rejection flag and some increment the manual checking flag. On testing, we can see that if the user borrowed any part of the down payment, the loan is automatically rejected. The knowledge engineering systems created through the invention may be changed as expert knowledge evolves. In this case, let's change the outcome of that declaration to flag the loan for manual review rather than to reject it outright. Instead of just testing it, this time we'll create the automated underwriting system as a separate standalone application that may be easily distributed to loan agents. Now, assuming there is no other reason for rejection, when the borrower indicates that they borrowed part of the down payment, their loan is flagged for manual review. Further changes may be made by the subject domain expert at any time.